Hello! In this video I'd like to show you how to use the AGGIOS EnergyLab tool to estimate and measure power for an NXP i.MX 8M Plus. I will also demonstrate how to optimize the power consumption of the i.MX 8M Plus using the Seed firmware. Let's take a look at EnergyLab. EnergyLab is an integrated development environment for creating and analyzing power models of your system based on the IEEE P2415's UHA standard. EnergyLab is also used for configuring and generating the seed firmware for your target. On the left, we see a choice of different views of the model. By default, it's a view of the system hierarchy. I have already loaded a model of the i.MX 8 system, so this is what we see here in the central area. We've got the NXP EVK board at the top level containing the i.MX 8M Plus SoC, as well as other board components such as the PMIC and the DDR chip. If we take a closer look at the i.MX 8 SoC, we can see its different subsystems, including processors, buses, memories, and peripherals. The IEEE P2415 UHA model contains all the power-related details relevant from a software and system developer's point of view. In addition to power states and power models, it also covers transitions and latencies, and most importantly the dependencies between different components, as well as dependencies on the clocks or voltage trees. Incorporating dependencies ensures that during simulation only states are entered that are feasible in a real system as well. The UHA model can easily be extended to cover your particular configuration, from application-specific peripherals to a complete custom board or system. But aside from modeling the hardware, EnergyLab also lets you model your software as UHA tasks in order to accurately reflect your application use cases. A task expresses the software's dependencies on the hardware as well as on other software such as operating systems or middleware. The use case we are looking at here is software-defined radio, which requires the device to be in the lowest possible power state most of the time, but then quickly wake up when a valid signal is detected. We have created tasks relevant to our application here, such as the tone detect task. This one requires the Cortex M7 MCU to be active, along with other components including the AXI bus. EnergyLab lets us follow the dependencies via hyperlinks, so we can jump to the AXI component where we can see the additional dependencies this component has. Now that we've modeled our system, including its hardware and software, we are ready to start the simulator. Once the simulator is generated, the EnergyLab simulation window appears. This window is organized like a debugger. On the left, we see the scenario file, which essentially is a sequence of timestamps and events. Using the control buttons in the toolbar, I can run or step through my use case. You will notice that our plot area now shows the computed energy profile for our use case. EnergyLab now lets me see more details such as the top consumers in my system, or the transition latencies, or details about the state of a particular component. EnergyLab has many other features that make it easy to further optimize power for your system. But now I'd like to show you how you can apply such optimizations to the actual target device by configuring and generating a customized Seed Power Management firmware. The Seed configuration dialog allows me to choose from various optimizations, either globally or individually, where I can enable features such as frequency scaling, letting devices enter optimized idle states when unused, or by scaling the voltage of the main supply rails. It essentially allows me to enable complex power optimization features from a user-friendly UI. Additionally, you can use EnergyLab to define custom scenes for your use case, which I have done here for the software-defined radio application. I will now include those scenes in the generated Seed firmware. Now all that's left is the generation step. The output is a seed.elf file, which is what we load onto our target. And now finally we can connect to our target using the test and measure feature. This feature lets me connect to the board that I have on my desk. The board is an i.MX 8M Plus EVK featuring a power sum module. The power sum module has additional power measurement infrastructure that EnergyLab can connect to in order to extract power measurement data. The seed firmware that we generated in the previous step is copied onto the SD card and then loaded on boot. So let's take a look at the EnergyLab Power Monitor. We can see the measured power in graphical form on the left and in a table on the right showing all the individual voltage rails that we're getting from the power sum board. We can also enable the Seed monitor to show additional details about the state of the system, which is very helpful for power debugging. At the bottom we see the different terminals, and in the Linux terminal I'm starting the SDR demo, and I also get Seed ready for the SDR application. Now as soon as the software-defined radio application starts, we see the system entering a low power state with just under 100 milliwatts in the SOC domain. The short 200 milliwatt spikes that you can see indicate that the M7 has been woken up by an incoming signal, and when the signal has been confirmed to be valid, Linux is woken up to do the signal processing. This can be seen by the 1.2 watt power consumption in the power graph, but also in the active state of the Cortex A53s, shown in the Seed monitor. As soon as the processing is done, the system goes back into a suspended state where only the M7 is active and occasionally checks the validity of an incoming signal. Depending on the ratio between the active state and the low power state, this optimization can save more than 50% in overall power consumption. I hope you've enjoyed this video. If you'd like to learn more about EnergyLab and Seed, please visit our website at aggios.com and watch our other videos on the AGGIOS Inc. YouTube channel. Thank you for watching.